Selamat pagi, Indonesia. I'm Brendan Burns, Corporate Vice President in Cloud Native Open Source at Microsoft Azure and a co-founder of the Kubernetes Open Source Project. And I'm really excited to have a chance to talk to you today about containers past, present, and future. I think it's really useful to start not with the history of containers, but actually with my own personal history in open source. The truth is that I've been involved in open source for more than 25 years, starting from some very early days when I was installing NetBSD on some discarded hardware from the school computer lab, exploring my way through mailing lists and IRC and the sort of community of the time, all the way through to working on open source projects like Quake 2 when it was ported to Linux, the Apache JMeter project for load testing, creating my own open source projects like the DroidDraw tool for designing Android GUIs, as well as doing graduate work in robotics that focused on a lot of open source technologies for both simulating the robots and the motion planning themselves. So I've been around open source for a really long time. I've had the pleasure of creating a number of different projects, seeing people come and find utility and community in sharing the development of these applications together. And I think it's a really key part of how we build together, not just as developers, but as a worldwide community of people who are creating cloud-based services and reliable distributed systems. With that in mind and a little sense of my own personal history with open source, I want to move on to talk a little bit about the history of containers. The truth is that containers, or what we now know as containers, is a combination of technologies and developments that have been around for a long period of time, starting with the earliest days in BSD Unix of the chroot system command, which was enabling processes to change the perspective on their file systems. Containers have had an approach which says we want to isolate parts of the operating system, or we want to isolate parts of what it means to be an application running on the operating system from the core details of the operating system itself. And I think this idea of providing an application-oriented perspective is a key part of what became containers that we use today. From changing the file system, to isolating it from a security perspective with jails, to isolating its resource usage with C groups, and then finally with this idea of orchestrating multiple processes in containers spread across multiple machines with Kubernetes. And I think it's interesting to see that Docker and Kubernetes in 2013 really are the things that popularize these ideas. And I think it's not just because of the technologies involved, but actually the demands of the applications that we were building and the ways that we were distributing them across multiple machines. When I think about a container itself, what really made it take off was this idea of a developer-oriented package. As we moved from handcrafting applications on top of individual machines and moved towards a world of continuous delivery and automation, it became extremely useful to be able to have a single package that ran the same, whether it was on my laptop or running up in the cloud, and it was oriented to the ways that a developer were thinking about building their application, not the way that perhaps a system administrator or an OS designer was thinking. I think one thing that was also really useful in the development of containers was that it was agnostic to language or environment, right? I think earlier on when people talked about packaging, it might be a WAR file or a jar file or some other sort of package that was deeply tied to a specific language or a specific runtime. One of the major benefits of containers was that, you could come together as a community around this package and have Java developers speak the same sort of packaging language as Python developers, as C++ developers, as Go developers, and really as anybody building any sort of application, whether it's a simple shell script all the way through to the most complex application binary. And that means that we can build a broader community. And if we build a broader community, we can identify this as a point of abstraction. And that's the final piece of the container, which is when we, as the developers of Kubernetes, looked at the container, what we really saw was that it was a runnable thingy. It's a point of separation and abstraction from the developer to the systems orchestrator. I don't have to worry necessarily about how your application is designed or how your application is built, but instead I can focus on saying, if you hand me this package, I can do interesting things with it. And I can build APIs that go beyond, what you are capable of doing with an individual process on an individual application. So thinking about that API, the development of the Kubernetes API really represented an explicit evolution of cloud-based APIs. Previous to the development of Kubernetes and container orchestration, the APIs that we had in the cloud were really oriented around specific infrastructure, a virtual machine or a virtual network, a virtual disk. They were all analogs for the things that we put into our physical data centers. They weren't oriented around the way that a developer was thinking about building their application. They didn't think about replication. They didn't necessarily think about services or load balancing or zero downtime updates or sort of all of the concerns that a developer might have about how they package their application and put it out together. With the development of the Kubernetes API and its ubiquity now in the public cloud, what we see is that developers can consume APIs that are oriented around their practices. You can do a rollout of your application in the API. You can define microservices that interact with one another. You can define paths in HTTP that route different requests down into your application. And as the ecosystem has evolved, we also see things like service mesh, GitOps, and more rising up to create even broader sets of APIs that empower our developers to do more than they ever thought possible. Let's take a look at some of the value that developer-centric API provides. I think the first thing that it provides is the value of a dev-centric package. If you looked at a VM image and you compared it to a container image, there's a lot more that we can do with that container image. And the reason for that is because the container image is tightly focused on a single application. If you asked a question like, where did that binary come from in the context of a virtual machine, there may be hundreds or even thousands of binaries coming from different places, all coming together into the operating system. And in the context of a specific application, many of those binaries aren't even relevant to the application itself, or even provided by the application itself. If you instead look at a container image, everything that is in that container dev-centric package is focused on running a single application. And so we can really ask a question like, where did that binary come from? What is the provenance or the authorship of the different components that come into that application? And this enables us to establish ownership and chain of responsibility all the way back to the very base that the container image came from. And that enables us to have a very secure picture of both where the source code came from, as well as any vulnerabilities that might be running in it. But it's not just about the dev-centric package. It's actually also about the dev-centric API. Because when you combine a container package that allows you to understand its history and all of the components that it's made of, with an API that allows you to introspect and ask questions like, what's running in this system? Suddenly you see that the visibility that a developer or an operator has into what's going on inside of a Kubernetes cluster is far better than what they might have had if they looked at a virtual machine. I can ask a question like, what are all the applications that are running in this cluster? Whereas if I looked at a virtual machine, at best I could do things like port scraping or other kinds of introspection, and I would have a much rougher, less declarative understanding of what is running in my cluster. And of course, a better understanding of what is running means better operations, means more security for both your developers and for the people who are responsible for ensuring, the reliability of the overall applications in your portfolio. Give an example of the kinds of value that you can get out of this. It's really interesting to highlight policy as a particular piece of the Kubernetes ecosystem. Policy is not something that existed at the very beginning of Kubernetes. It's something that has come to be added. And its need is clear when you think about the fact that, while RBAC can allow you to have access or not access, authentication allows you to have access to the cluster, it doesn't do very much to ensure that you do the right things. For example, how do you make sure that every developer gets a security review, or only pulls images from your private registry, or even provides you with metadata like, what is the business that is running this particular service? The way that you do that is with policy, which has the ability to introspect individual pieces of your requests to create a deployment or to create a service as they're coming into the Kubernetes cluster. And then it can make judgments about whether this is a valid request or this is an invalid request that go beyond the basic semantics and actually start implementing best practices for both security and reliability. I think that when we think about policy, sometimes we think of it as sort of a boring piece of compliance or a traditional IT way of doing things. But what we have seen more and more is that policy is a really rich tool to help the developers naturally move in a path that leads to quality applications. And this has led to the development of the idea of guardrails within the Azure Kubernetes service. The idea behind a guardrail is we have in Azure 5 or 6 years of experience watching our customers run Kubernetes in production. Now, what we've seen along those years is many different ways that they can cause themselves to have outages through accidental misconfiguration or not following best practices. We've distilled a ton of that learning down into these guardrails that can be implemented using policy enforcement, such as you can require that your developers always specify liveness or readiness probes. There's nothing in the Kubernetes API that requires that all of your pods have liveness probes. But of course, I think we all know that your application behaves much, much better if you write some custom code that assesses whether the application is healthy or not. That little bit of information enables Kubernetes to do a much better job managing your application. But it's a hard thing to train your developers to do. If you instead install a guardrail that requires your applications to have those liveness probes defined, well, then you know for certain that your developers cannot deploy applications that don't have that best practice implemented. And there's a bunch of other of these examples, each of which we've seen cause outages for our own customers, and sometimes for our own services that we've taken and coded into these guardrails and made available as enforced best practices within the cluster. Of course, just like with linting or any other sort of style guide, we understand that not everyone is going to want every single one of these guardrails. And so, of course, you will have the ability to opt in to the various guardrails that make sense for your organization, and even to define new guardrails that are, rules that you want to implement that perhaps are not things that we've noticed in the breadth of our customers. I think this is a great illustration of how a tool that might have traditionally been used for enforcement of corporate policy can be broadened to really bring best practices to the developer community. And of course, all of this work is done in the context of open source. The Gatekeeper project that we initially developed to implement Kubernetes policy was donated to the CNCF. And here on this slide, you can see all of the different projects. Actually, it's not even all of the different projects that Microsoft works on, from things like Dapper for packaging and developer runtime, through to scalability tools like the Kubernetes event-driven autoscaler, our work on Draft, and the extensions for VS Code that enable Kubernetes developer tooling. I think the most important thing through all of these contributions is the fact that they're available to anyone in the Kubernetes community. They're not locked to our cloud. They're not specific to our cloud. They really are our attempts to participate and innovate out in the open to benefit everyone in the cloud native ecosystem. And I think I'd like to highlight some of the value of doing this sort of stuff, especially on the developer productivity, by looking at the Visual Studio Code extension that we've built for Kubernetes. One thing you can see over here is that it gives you a really useful tree view of your cluster, very easy to explore and understand without having to teach people a lot about the kubectl command line tool. More importantly, it uses commonly recognized paradigms like a right click to discover more options for what you can do with a container that's running in that cluster. And I'd like to highlight one particular one, which is port forwarding. One of the things that we see and actually just saw in a customer cluster is that people accidentally put things on the internet when they're deploying to Kubernetes. And I don't think that this is because, they want to be insecure, but rather because Kubernetes sometimes makes it challenging to understand, if I deployed something, well, how can I sort of poke at it? The right answer and the best practice for doing this is using secure port forwarding, but it's not necessarily easy for a developer to discover that. By integrating it into a context menu that's available when you right-click on the pod in this UI, what we do is make it easier for developers to fall into that pit of success and avoid things like this. right? So if we can prevent mistakes by making it easy to be secure, we can do a much better job of ensuring the security of your applications and that your developers follow the right practices without them even noticing that they are, being pushed in a particular direction. I think true security, true reliability comes when developers do just the right thing without even thinking about it. And so through guardrails, through our work in developer tooling and beyond, we're really focusing on building that funnel that takes people down the right path. And of course, like everything else I mentioned before, all of this work with the Kubernetes extension is out there in open source. And if you're interested in learning more or participating in the community, strongly encourage you to come and check it out on GitHub and get involved. Another example of our collaboration in open source revolves around GitOps, and in particular the Flux project. And what I like about this is that not only is GitOps a really powerful way of managing your systems, which we'll get into in just a second, but it's a great example of our involvement in open source in a project that we didn't necessarily create. Right? I think we highlighted a number of things that we had created for the open source community from Azure before. But with Flux, when we looked out and we saw people who wanted to do GitOps, what we said was, you know what, there's already a great project out there. And we want to get more involved in an existing project, not necessarily feel like we have to have invented everything ourselves. And so via, our contributions to Flux and obviously the direct connection between GitOps and GitHub, we've developed a really great relationship out in the GitOps community and also brought it back into the Azure product to help our own customers do GitOps in a supported way within the Azure Kubernetes service. Now, you might not have seen GitOps before, or maybe you're a GitOps pro. I wanted to go into a little bit more detail on why you might be interested in GitOps. And I think to highlight the problem, what I really like to highlight is that in the clusters that we see developed and deployed out in the real world today, the truth is that there are many different teams that own a piece of that cluster. Perhaps your security team is deploying scanning or intrusion detection software. Your platform team is deploying monitoring and observability software. And then, of course, there's application teams that are deploying and managing their own applications inside of that cluster. Now, if it were only just a single cluster, it might be okay for each of these teams to have credentials to the cluster and to be simultaneously pushing things out to the different applications. But the truth is that in any large-scale deployment, there isn't a single cluster. There's actually lots and lots of clusters. So what we see is instead of a single Git repository or a single set of applications, we have a repository for each of the teams. And we have a lot of different clusters that need to look and feel exactly the same. And while I have a single application team shown here, in reality, many of these clusters will be running different sets of applications depending on the different application teams, but they will need to have a consistent platform and a consistent security install, right? So pushing the right configurations to all of these different clusters all at the same time is a very complicated thing to do and very hard to get right. And more importantly, it also requires that credentials for these clusters be shared across all of these different teams. So the GitOps model sort of flips this on the head, and instead of having the teams push their applications into each cluster, instead the Flux infrastructure for doing GitOps runs within the cluster. And in every single cluster where Flux is running, it's monitoring all of the different Git repositories that are maintained by these different teams. So for the security and scanning software, it's paying attention to the security team's Git repository. For the platform infrastructure and application infrastructure, it's paying attention to the application team's Git repository. And for the platform observability and monitoring, it may be paying attention to the platform team's GitHub repository. And what I've shown here is just in the context of a single cluster, but of course this is repeated for every single cluster. And this builds a much more scalable approach to simultaneous management of all of these different applications, because each of these teams can independently push code or push configurations to their GitHub repository and across all of the clusters in the fleet. and there could be many, many more than the 4 that I illustrate here, they will all immediately take those new configurations and apply them. It can happen asynchronously, and more importantly, it can happen without these teams necessarily having credentials to make the changes into those clusters themselves. So it's both a more scalable and more secure way of managing this intersection of lots and lots of applications coming together in a fleet of Kubernetes clusters. I think the other piece that we're really fascinated with, in addition to enabling developers and application platform owners to scalably take their applications out to multiple clouds with GitOps, is helping developers sort of scale the Kubernetes cliff of complexity. I think that while Kubernetes does a tremendous number of things to make operating applications at scale easier, it hasn't necessarily reached its potential in terms of making developing those applications easier. And so we spend a lot of time and energy helping people scale the Kubernetes cliff. And the picture that I like to put in mind is this definition of the new PaaS, or the new platform as a service, that we see developing out there. It's based on a foundation of Kubernetes with modular components shared across applications that are running from Helm charts, running from operators, running from true platform as a service like Azure Container Apps, or even just YAML files that individual developers created. And I wanted to dive in a little bit into this modular infrastructure that we're building out in the open source to support this new platform as a service. The first is KEDA, or the Kubernetes Event-Driven Autoscaling. It really is focused on autoscaling made simple for Kubernetes, and it's driven by events rather than resource usage. So for example, you might want to auto-scale a processor that is analyzing images for every image that a user uploads. So every time an image is uploaded, you're going to scale out your image processing. If no images are being uploaded, you'll scale down to 0. There's a huge catalog of scalers that have been built out in the KEDA community. This originated with Azure and Azure Functions, but it's seen broad adoption by a bunch of different users out in the cloud native ecosystem, and we're really excited that it is a really vibrant part of the cloud native compute foundation. Another great example is the Dapr project, or the Distributed Application Platform Runtime. Dapr is really oriented around helping languages written in any programming language access a consistent set of APIs for cloud native patterns. One of the things that we've really struggled to do in the developer ecosystem for cloud native applications is share code. We have lots of great ideas about how we build distributed systems, and you can read books and articles and watch videos, but we have not done a great job of taking those patterns and practices and encoding them in reusable libraries that everyone can use, no matter what programming language they're in. Dapr really intends to change that by developing a sidecar that sits next to your application, is accessible from a broad variety of languages and even raw HTTP or gRPC, and implements the best ways of accessing NoSQL stores, actor models, event-driven applications, and many other common distributed system patterns. We really see this as a path forward, and of course, as with everything else, it's an open source project that has a rich community of not just people from Azure, but people from throughout the Cloud Native Compute Foundation contributing ideas and best implementations that you can take advantage of today. I wanted to take a last moment to glimpse into the the future that is beginning to be here, but is much more speculative. And I think all of the things I've talked through so far represent actual things that are out there in production that people are using today. The next couple of things that I'm going to talk about, people are using, but they represent a little bit more of the bleeding edge of where technology is going. The first thing I wanted to highlight is eBPF, or the Extended Berkeley Packet Filter. It's actually way more, though it has packet in the name, it's actually way more than oriented around just network packets and processing. It's a way of injecting code inside the Linux kernel, and actually increasingly the Windows kernel as well. But one of the things with these new technologies is that while there's a ton of promise, it's sometimes very hard to realize for a person who's just developing an application. What I'm really excited about is this project that we've worked on called Inspector Gadget that's really intended to make eBPF easy and accessible to developers wherever they are. And if you check this out, it's basically oriented a bunch of eBPF programs into this idea of a gadget. And a gadget is something that does a useful task. For example, auditing system calls, tracing system calls, doing top for networking or CPU. And all of these gadgets that are focused around specific tasks are easy to deploy using a kube control plugin. So you can very quickly gain access to the power of eBPF without necessarily having to understand the details of how to build one of these applications inside of the kernel. And again, out there on GitHub, in the open community, with a bunch of people from Microsoft and other places contributing to these best practices for intersection of eBPF and developer-oriented debugging and tracing tools. The final thing I wanted to talk about was WebAssembly. We see a lot of promise in the WebAssembly work that is happening. And I think that the most interesting thing to think about here is that we have an opportunity in WebAssembly to perhaps define a new container format. The truth is that when I started at the beginning of this talk, I talked about the history of containers and how it's built on this technology that has been around for quite a while. So while the cloud native applications that we've built in Kubernetes represent a really new way of building things, the building blocks for the containers themselves are actually quite old. With WebAssembly and WASI, which is the WebAssembly Systems Interface, we actually have an opportunity to redefine what it means to be a container and what it means to be an application in a cloud native way. And so instead of relying on the tools of POSIX APIs and operating system concepts that date back to single machine systems and even to mainframes in some cases, I think that WebAssembly represents a really interesting new opportunity to truly define what a cloud native kernel might be. And with that, I'd like to conclude. I'm really had a great time giving you a glimpse of the past, present, and future of Kubernetes. I hope you enjoyed it. And I look forward to seeing you in future cloud native events. Thanks.